It works. Okay. All right. So today I want to talk about some more fundamental stuff, actually, right? Some of these terms that you may have heard if you have looked at complex systems as a framing. So emergence, and we'll see. Emergence is the big thing I want to talk about. We'll hear some interesting stuff about how science possibly will kind of unfold as we go further into the future. So I've talked about this golden age of reductionism, right? So we figured out the atoms, and that's it. You know, you can't make it up in any other way. That's what we have. We have quarks, atoms, and so on. And we have DNA, and that's the story. And kind of we're figuring out how those things fit together, right? So the sort of the greater part of science, as I've said, this manifesto thing, is that there's a helmet. Is systems, is understanding how things fit together. Okay. What else am I trying to tell you here? So I want to tell you, so we'll get to that. Couple little pieces to start with. All right, so assignments, we've had them. So online are these new episodes for next week. All right, so if you click on this, you can, at your leisure, possibly not pleasure, look at these. There's this thing, there's a piece on random walks, which is unfortunately a full kind of lecture. It's 74 minutes long. Okay. And then there's a small piece here, which is just 17 minutes. So I called them lectures, or episodes, but they're of a piece. They fit for this one set of slides here. Okay, so there's lots of fun things in here. There's Plinko, I mentioned Plinko, a little piece about stock market returns and so on, and randomness. And so just to show an example of, I mean, this, you know, a lot of ways we have to just touch on a few things, but one of the things that comes out of here is that randomness gives rise to structure. That's a very important part from a general science point of view, and very unusual structure. So you'll see that for first return walks, right? So this lecture is going to be about, here is the local establishment where your friend, this is in no way you, or in fact someone you don't know at all, is drunk, and they leave and they start to wander around randomly, right? And you're worried about them, so your question is, when do they come back? When will they come back? Right? So they're going to lurch. So if we put time here, and this is x, they're going to be lurching. Right? There's going to be this kind of lurching thing. 50-50 chance they'll move left or right. So after one step, there's a 50% chance they'll come straight back. Right? Fair enough. So you'll see them again. And so you'd think, all right, well, you should see them a lot. But it turns out that what we'll call the distribution of first return. So what's the probability they return after time t? Right? So it turns out to be one of these terrible parallel things, and it turns out to be that the average is infinity. The probability is 1. You will see them again, but the average time will be infinity. And that's coming out of random walks, and this is why you should never gamble or bet or go to Las Vegas, or you should be Las Vegas, alternately, because people don't understand probability. If you do, you can make a lot of money out of other people. Farm other people. Isn't that lovely? Anyway, so that's Wall Street. Anyway, so that's a piece in here. There's some other things in there. Yes, there's some stuff about Doctor Who randomly moving around the universe. That's another funny distribution. But that's about transformation of variables. So you get the story is basically a very nice, benign distributions like exponentials and Gaussians. These are things that just appear for free. We're quite happy about them. We have lovely explanations. If we see one on the street, we're like, that's fine. That makes sense. And then we have transformations of variables. So the system has a couple of variables associated with it. One variable is described very nicely, say by an exponential. Another one that's connected to that variable will be described potentially by one of these parallel size distributions, right? So you have a reasonable thing, a very reasonable connection, and then a very scary, weird thing comes out the other side. So it's another kind of source of these distributions. It will matter later on when we talk about robustness and this thing called highly optimized tolerance. So that's incredibly exciting. Excited for you. Okay. So you can watch that whenever you want. But otherwise, we'll have Josh Bongard on the Tuesday and Bagro on the Thursday. And that should be great. I had a little piece appear today, so this is nice. It's a little, it's an article I wrote here. We'll talk about some of this in the course, but it's homo narrativist and the trouble with fame. There you go. Anyway, so you could read that later on. PoxVox tweeted it. A thing that I'm not really independent of. Okay. Okay, yeah. So that was good. That took a lot of, that was somewhat painful. But anyway, now it's actually, now it exists. All right, so episodes, good. So I'm going to talk about, as I said, this kind of fundamental stuff about complex systems, and then I want to talk about projects. And I want to just sort of give you a few examples of what you might want to work on. In doing that, we can just sort of explore a couple of things that have been done. A number of things have been done recently that are, incredibly fantastic and fun. Again, it's all this stuff that's opened up for examination and exploration. Lots of great science in the last 10 to 15 years. Lots of bad science as well, but that's how science works. All right. Okay, so this was the manifesto, all right? Golden age of reductionism. We're trying to understand how things fit together. We've been doing it for a while, but we're really in the game now because of this sort of thing. I talked about very simple things, right? So we have computation now, so we can store data, we can analyze things, we can simulate, all these good things. So here's some of the sense of, this is from The Economist. This was actually published in 2009, and you can go to the article, and it's kind of an interesting thing to, 2010, I guess. You can sort of see how this fits now with where we are. This was an estimate of where the traffic was going to be. We're getting up to zettabytes, right? And then there are yottabytes. Yottabytes are next. So NSA has been building a very large thing in the Utah desert to store something on the order, I believe, of a zettabyte. Of course, there's been some discussion about that recently, but that's been known for a long time about this building of a big thing. Trying to make it easier for them by recording things. So why not? So we have crazy things, right? So the Large Hadron Collider, which could kill us all, 40 terabytes a second, of which they throw most of it away, right? Because they know. What do we get for Twitter now? What do we get, per day?
Per day, I'm not sure. It's like you compress it down to a couple of eggs, like
per.
I'm not sure.
Okay, we need to know, but it's actually quite a lot, but it's. We don't get this much. Yeah, it's nasty, right? Yeah. Let's see. So LSST. So this is astronomy. This is going to come online in 2016. Is the projection for it? 140 terabytes every 4 days. So this is, and so we're getting a full sample of the sky, I think, every 3 days. These numbers, of course, are more now. I need to upgrade them probably. Facebook, just an enormous number of photos, which they very cleverly mine for information about what's behind you. Very clever. That's why they bought Instagram, I think. So tons of data, and there's all sorts of areas where, and I've talked about this transition from sparse to rich data set. This is a bit of a problem in this graph, as you can see, right? So information created, available storage. So there's a lot of things, a lot of things should be lost, but it's good to forget. Looks like we're going to have to forget. Psychologically, it's good. So we've gone up through all of these things, right? So we had a terabyte. So terabyte is monster, right? When we decided we needed another thing above gigabyte, we went for terabyte because that was enormous. And there's some nice estimates in here, right? So Library of Congress is 15 terabytes, although they're trying to fit Twitter into the Library of Congress now, which completely transforms their data storage. So a few years ago, right, they said, the Library of Congress said, oh, okay, Twitter can be the microblog of record, right? So the New York Times is the paper of record for the US. Twitter becomes the microblog of record. So they said, well, we'll store it, and maybe we'll have a computer and you can come in and look at it or something, right? Right? We can do that. So I don't know if they've got all the data there yet, but it's taken several years of figuring out that this is basically an incredibly hard, messy, nasty problem. Twitter themselves have had to cope, of course, with having their own data sets. They've evolved over time. So, really pushing ourselves to the limit. So petabytes, we've had them for a while, exabytes, zettabytes, and yottabytes. These are really gigantic things, and it's, presumably there is a limit to this. We'll look at scaling later on for memory and all sorts of things, but yeah, lots of data. Okay, so
you should add that they don't have a prefix
The next one after that. No, I don't think so, right?
Right.
Yeah, right. We've got to make it up.
Yeah. I want that job.
Framing is everything, although now it's sort of, lost it, right? Terror was great. That was pretty. But now it's just going to be nonsense words. All right, so, okay. Right, there's only so small you can go as well, too, right? So we get down to plank scales and so on. We're like, okay, that's enough, we don't need more words. Okay, so this is just, again, just an example of the kinds of things that have happened recently that are really, really very, very different. So this is, well, a somewhat famous paper. I mean, there's a ton of, if you haven't seen this and you're interested in this, there's a lot of things to read, to look at in here. So it's science, yeah, so it's a couple of years ago now. So this is the n-grams data set, right? So Google has been, I don't know how nicely they do it, but I think that they cut the books and scan and, right? So if you, when you're entering a password and there's the little captcha thing and the reCAPTCHA. So the captcha is just, are you a human, right? So you have to enter your little, this funny looking word. If there are two of them, you may have seen this, right? So I'm sure you've seen this. If there are two of them, one of them will be to help Google or something, to translate a word, right? So they'll ask people 50 times, what's this thing that I can't identify? And you'll see it has a diphthong in it or something. There'll be something a little funny about that one. So you can lie about that one because it doesn't know. The other one is to test you, and this one is getting you to, like you've got a few brain cycles. People are lying around with, these brain cycles that aren't being used, and they're being harnessed. Isn't that lovely? So, but you're helping with this project in particular. Actually, some of those recently, you start to see they have street numbers, which is, I mean, pretty brazen. It's pretty brazen. It's obviously someone's, there's a picture, one is a squirrely word, and the other one is, someone's house number. So it's Google Street View is, finding the number, sending it off to other humans to innocently help. It's really extraordinary. I mean, it just seems a lot. Anyway, okay, all right. So Google n-grams, so you chop these books into bits and scan them and translate them with this kind of extra funny process involved, this socio-technical translation. But just optical character recognition and then people on top. So for every year, they have a data set, and it's a very rich data set. It goes back to the 1400s, 1500s. It's really 1800 to 2000 is pretty good. Many different languages now. And it's not, so the books aren't there, but what they've done is put up in various ways, 1 grams, 2 grams, up to 5 grams. So, which is a bit odd. Today is a bit, I'm going to tell you about fun things. So it's, for example, will end up as a 3 gram. It will be broken up into, in the original data, so it's changed now, I think, but it's a bit of a funny problem, right? So if the end of a sentence was cow, jump, I don't know, then, right, the something off like this, they break this into a 3 gram, cow, period, the. So it was a fairly reasonable, I mean, odd, but at least very clear way of breaking up text. So you end up with mountains of text for each year. You have the number of times a 1 gram appears, a 2 gram appears, a 3 gram appears, and they become more and more obscure as you get out to 5 grams. I think they have the number of books they appeared in, the number of pages they appeared on, right? So it's a pretty rich data set. All right, so you can do all sorts of things, and there are a couple of examples here. So this is just simply the mention of a year. So how often does the number, and we think it's the year. So this is 1883, 1910, and I think 1950. So in the English corpus, and it's different if you look in, say, English fiction, for example. There's American English, blah, blah, blah. You see this spike. No one really talks about the future beforehand, and then it starts to decay. So the upshot of this little figure, the claim is, and you have to be careful with this because what's happened later is that a lot of technical documents have been fed into this thing, right? So all sorts of computer science things and so on. But you see the texture of things changing. So, and they have a viewer online. If you haven't played around with it, it's quite good fun to play around with. You see the world wars have very clear impact on the overall thing of the culture. What you see is this decay here is faster. So there's this sense, the claim is with this, is that cultural, so the now matters more, but cultural memory is compacting, right? Which You see in citation structures as well, so knowledge is building, right? We're getting more and more papers at this kind of, it's growing at this ridiculous rate. But you see the way that that knowledge tethers back into the past is shrinking as well, right? So it's a shallower connection back into the past. I mean, some of this work was done in the 70s, and we'll come back to it later on. Beautiful stuff, but again, people counting things. We can do much more now. So these are okay. So they got cohorts of famous people of different types. So there's political figures. It's a little hard to read this. Actors, I think biologists, artists, I think, and mathematicians down the bottom. So you find them. They're famous by some. They've defined that themselves. And then you look at how much they're mentioned as a function of their age. So political figures, right? So this is 50, 60. This is when they're truly famous. Mathematicians are just hopeless, which is correct. So well done, humans. Physicists and chemists are down here. So Einstein didn't really affect that one. And I think that's authors, right? So authors are sort of taking off. This is censorship. This is a sense of censorship. So this is this is the English talking about a group of a selection of people, artists and authors and so on, versus the German, a very different kind of mentions. You can see this kind of gap in the middle in the Second World War where there's basically suppression in a sense. Like they're not. This is looking at German text. People like this is Pablo Picasso and so on. They're not being talked about. It's really the inset there is probably the better thing. Okay, so there's a ton of different stuff. So this is not a perfect thing, but the lenses we have now that we really have to look at and play around with, great fun. Okay, I like to say this. So Lord Kelvin, very famous physicist and scientist in general, bold statements, to measure is to know, right? I mean, it's a sort of a surprising thing. I mean, people forget to measure things or move away from it. And I think what happens actually in fields where you can't measure things well, theory flourishes, right? Theory just goes off in all sorts of directions because it's unimpeded by reality. And then a very important thing, if you can't measure it, you can't improve it, right? So this is all great. One of the problems we end up with in general, though, is that the things we tend to measure become the important things. Or the things we can measure become the important things. This is a big problem in engineering. Right? So you could improve traffic, for example, traffic flow. Very measurable. Right? So you can make a fantastic thing. And when I was a kid, I remember thinking, I grew up in the desert, basically. And I remember visiting a city and thinking, because all the turns were hopeless, I was thinking, well, you could have you could have something like this and this sort of thing, and you could make it right. You have all these little ways of, if you had a crossroad, you could have all these little ways of connecting from one side to the other, and okay, which is the horrible things that you have on giant freeways and so on. Right? But it would be good. It would make it efficient. But it's a horrible thing. It's a horrible thing. So you can't. It's harder to measure. It's harder to quantify quickly or easily how people feel about things. For example, is it a good place to walk around? So that's one example. But we tend to get a little excited. I like metrics. I love measuring things, but it is something to always reflect upon. You kind of need to have a list of, here are the things we measure. They're all important. Here are the other things that are important we can't measure. We just need to keep them on the list because we tend to forget about them. Sorry. My little ranting. Okay. He said other things. X-rays will prove to be a hoax. Got a little excited about physics. Nothing new to be discovered in physics, right? Just better measurement. Okay, so, in the classic way of cherry picking quotes from people who said lots of things, you can do okay. So quantum mechanics was surprising, probably. Would have been. Chaos would have been very, very concerning as well. And this is also, this physics explains everything kind of story, which is just a disaster. No good, right? Physics, you're running around with your atoms, you're not going to predict DNA. You might predict something, you might start to get to thinking about life properly and so on, but the specifics of things, no. This was to show, and this is the engram viewer, this is to show the rise of the term scientist, actually. So this is 1800. This is 1800, so this is scientist, actually. It's got a little bit of hurt right now, but this is it's a modern thing. This is 1870 here, you know, right? It's modern. And so there are a few others in here: mathematician, biologist, physicist, sociologist, and a thinker. Okay, thinker did okay, but oh yeah, mathematicians have been lurking around for a long time. Very cleverly, sort of, you know, dressed in druid clothing or something, and talking about God and saying it's kind of, you know, just doing a little bit of math, but God is good too, and you know, right? Okay. You know, medieval stuff is great. Okay, so it's you know, science is kind of a new thing. All right, so okay, fine. So I wanted to talk about that sort of backing out the manifesto thing. You guys know there's lots of data. I know you do, but okay, so big transition. So emergence. So it's a term that people get very confused about, and kind of I don't know why, but so basically it comes from philosophy, actually, originally, and it's the idea that systems produce macro structures and macro patterns based on their the micro interactions. And this is an odd thing to say, yet, you know, yet still, this is of course Wikipedia from a few years ago, but it's a controversial subject. Well, not really. I mean, we know this happens over and over again, right? So, and again, fluids is the example I like to come to, because we derive analytically, we can derive analytically the Navier-Stokes equations from, you know, just a very reasonable kind of understanding of how things fit together microscopically, and we get very different behavior macroscopically, right? And that fluids are a great example of that. So we know about that. It's more as we get to less physical systems, one that involve algorithms. I'm going to say algorithms more, and I think life is algorithms, right? So you know, socio-technical systems, things involving people and platypuses and so on, then, you know, it becomes more unclear if you can describe it. And that's what we'll get to today. I want to sort of tackle this issue of, we've had a great time, really, where we can write down equations that explain lots of things, very succinct things. We may have to use a huge computer to simulate it, right? So we have to do that if we want to, you know, we have the Navier-Stokes equation. If we want to simulate flow around a jet, we have to basically put in the shape of a jet and simulate everything. But we can do it. We're kind of entering this time now where there are things like machine learning and so on that can do really clever things, reproduce things, make things happen, like maybe reproduce a system, but we don't have a simple story for it. We might not be able to understand it. So all right, so we'll hear something about that in this Radiolab piece that I want to play. So it actually comes from philosophy, which is good. So they've contributed a little bit in the last couple of 100 years, but not much. Okay, so let me get this to work. Is it going to play? Good. Okay, so this is from Sir David Attenborough. I grew up watching Sir David Attenborough. There's underneath this rock. He's really fantastic BBC shows, and just absolutely wonderful, right? I don't know if you've ever seen them, but in that kind of classic English way of speaking. And so this is actually a video of him, but it's Strogatz. Strogatz has some nice things to say here, so let me see if I can make this work. Strogatz was talking on Radiolab, which has had some good things. There's a link to it. Let's see if this works and doesn't explode the volume. Ooh. If you want to. You don't. Yeah. I mean, it's just a little video.
Fireflies are something that we have all loved as kids, right? Catching them in the backyard, putting them in a jar and watching them glow. So we don't tend to think of them as anything all that mysterious. Well, they do one thing very nicely, which is flash on and off.
That's all fireflies do, flash. But what interests Steve Strogatz, a mathematician at Cornell University, is that there are places in the world,
not here, but in Southeast Asia, in Malaysia or Thailand,
where fireflies don't just flash randomly, like we're used to. They somehow flash together.
There are enormous congregations of fireflies along riverbanks.
How many?
It could be tens of thousands, tree after tree, extending for literally miles along the rivers, all flashing in sync like a Christmas tree, rows and rows of Christmas trees all wired together going off. And it's one of the most hypnotic and spellbinding spectacles in nature, because you have to keep in mind it is absolutely silent. I mean, picture it. There's a riverbank in Thailand in the remote part of the jungle. You're in a canoe, slipping down the river. There's no sound of anything, maybe the occasional, exotic jungle bird or something. And you're looking and you just see whoop, 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 with thousands of lights on and then off, all in sync.
Because no one knows.
There are literally 10 theories.
What seems to be clear, says Steve, is there is no one firefly that makes it all happen. It just happens on its own. Order materializes out of nothing. And that has him puzzled.
How can order come out of disorder? I mean, this is what the creationists love to talk about. And it's because they don't understand, and neither do we. This is the big mystery of science. I think bigger than black holes or bigger than superstrings. I mean, science has had hundreds of years of success since the time of Galileo and Newton from reductionism, from looking at the smallest parts, whether they're genes or atoms, whatever. That's great. We need to understand the individuals. But that's not enough.
Okay, there's an ad for something. So, I think well framed, right? This is a we will have to understand those small things. Of course, we'll have to get to that eventually. We'll have to understand why we exist at all, and I have some statements about that. But how we go up through these scales is fantastic. And so, yeah, he's done a lot of stuff on synchronization, and of course has, maybe some of you know this, he has a great book on that. Okay, here we go. Okay, called Sync. Good branding. So, these things, right? Tornadoes, financial collapses, human emotion. You don't find human emotion sitting inside a carbon atom, but somehow, when we stick ourselves together with lots of other atoms, then we get into all sorts of interesting emergent behavior. I mean, it's pretty fair enough. Somehow we get from particles to everything that exists, right? Genes give rise to organisms. You have all of these links, all right? People, of course, people created the web, the religion, all these things. Language is fantastic. And so one of the games that we'll get to, we'll see, is that there are regularities in all of these things that you can start to say, well, this would have emerged whatever, right? For a bunch of octopuses hanging out together, we would have produced these things. Or this is specific to us, right? So that's a good thing to understand. Of course, when you need to understand, you want to create, right? So Aristotle, right? So the whole is, I always get this wrong. The whole is more than the sum of its parts. It's good, but Anderson's framing, more is different, is probably the stronger one. Schelling. Okay, so I want to show you a few examples from other fields. So that's a good basic physics problem, right? Synchronization. Really rich, good, fun thing to do. Actually, one of our students has now just produced a paper with surrogates on synchronization, who went through all these courses. This is the great Isabel. Schelling, so this is coming from economics, has the same frame, right? It's a much harder area. We know what the atoms here are people, and so that's a more complicated thing. One of his famous things is about segregation, which this is writing in the 50s. It's something that was happening and trying to understand it. All sorts of other pieces. So wearing hockey helmets, so, that's about ice hockey. That no one wore them, and no one would start to wear them unless everyone else was, right? So these collective action problems that people have wondered about quite a bit. Of course, we see collective action happening, and we need to understand, in some cases, how to stop it. In some cases, how to facilitate it. The seating choices thing is, right? People sit in funny ways in lectures, and that's, he has a ton of things here where he gives really nice stories for how they come about. So I'll play this little piece because this is a little, let's see if this works. A little cheesy, a little cheesiness.
4 decades ago, on a long-haul flight, the economist Thomas Schelling was doodling with a pen and paper and thinking about the problem of racial segregation. When he got home, he picked up a chessboard to continue his investigations. And you can do the same thing. Simply lay out alternating black and white counters, or brown and white eggs. Remove any 20 and add 5 just to mix things up a bit. The board now represents a mixed neighbourhood. Now these brown eggs aren't extreme racists. They're happy to live in a mixed neighbourhood, but they don't want their white neighbours to outnumber their brown neighbours more than 2 to 1. The white eggs feel exactly the same way, so take any egg that is outnumbered more than 2 to 1 and move it to the nearest acceptable location. As you do this, you'll find something astonishing happen. The brown eggs and the white eggs will separate out like oil and vinegar. Even a mild preference for the colour of your neighbour can lead to extreme segregation. Thomas Schelling's chessboard experiments became famous, and Schelling himself eventually won the Nobel Prize. For me, the experiments are about more than racial segregation. They show how, although we as individuals may be rational and we may be tolerant, the society that we produce together may be neither rational nor tolerant. That's why the message of the logic of life is sometimes so surprising. Yes, the world we live in is sometimes irrational, but we aren't.
Go away. A little bit cheesy, sorry. But I mean that's, so this only came about from a little algorithmic experiment. It wasn't done on a computer, set up a chessboard and put pennies and nickels and played around with it, and I think he got his son to do it, and they messed around with it over and over. So, you know, had to simulate it. And before that, the easy story to tell, the natural story that people would tell is that if you had segregation, it's because people just intrinsically didn't like each other, right? That they culturally didn't like each other. So here's another potential narrative, which you can only get to by running. Can't really do this by writing down differential equations. This doesn't come out of simple math, but you actually have to run the experiment. So, and he did, of course, he did it without computers. He did it on a chessboard. But this is a sort of, there's a lot of these kinds of things now, although this still remains one of the great examples. It's a very, I mean, this is an awful problem. But getting a handle on it, you know, being able to even just show that this other narrative existed was gigantic, right? It's a really, really important bit of thinking. So this is, of course, not exactly how real societies function properly, but the idea of this is a toy model, just simple ingredients, very important, right? We need to do these things over and over again. All right. So here's a character, so we have other people talking about these things. So economics, just the idea of emergence appearing here, so that some markets, for example, and we think of them as being very well defined, but they're continually, you know, being refined. Of course, we have problems, legal systems, are these growing systems, which, you know, could end up with good or bad problems. We talk about taxonomy, right? So this is stuff that's made. Cosmos is grown order, so this is just these two different types of things. So one is kind of a hierarchical structure, the other one is a decentralized one. These are these sort of limits of structures. These ones are these are good at doing a thing that's fixed, right? These are good at creating. And maybe you need to transition from here to here. That certainly happens. That's the story here. Once you've solved the way, you know, once you've figured out how to do something, you end up with a hierarchical structure. I mean, even physical ones, like branching networks, right? Supply blood to the body. Military, of course, is not really a hierarchy, but we like to think of it like that. Right, okay. So, you know, an example is the Dewey Decimal System, which is imposed in the, I guess it's the late 1800s. It's not this Dewey, it's another Dewey. So this is the way the world should be broken down, right? But was in his head. It evolves over time. This is a collective thing that's emerged in the last 10 years. You know, people tagging things gives rise to this sort of clouds of information around informational objects. And in many ways, it's more powerful, right? Coleman. Yeah. So a great thinker in sociology. It's not around anymore, but talking. So a lot of arguments in sociology have this kind of thing where you talk about the macro to macro, right? So there's a way that the culture behaves Here it's religion giving rise to capitalism, right? And that's a story that's sort of seeable or conceivable at a large level. This is much harder to deal with, but it's really somehow the thing that has to be understood. And so we have this, again, this funny thing where we're happy with this until we start to be able to measure this sort of stuff, and we're like, yeah, actually that does matter, so let's try to understand it. So we're very much struggling with this kind of thing now because we're getting these sorts of details about all sorts of things, right? People's choices, how they move around, all sorts of things. So because we can measure it now, we think it's important. But it was always absolutely important. Yeah. And our theories tended to fit what we could measure. All right. Coleman, famous guy. You should. I used to have a computer called Coleman. So you should, before the whole strain animal thing. So other people. So math. All right. So this is a bad thing. So there are bad kinds of complexity, not bad, but they're harder to deal with theoretically, where it isn't really a micro to macro story, where you have lots of scales interacting with each other, right? And so maybe biological and ecological systems are more in that basket. And we can get somewhere with these things, but they are hard to understand. We have Gödel, who was on the edge of sanity the whole time, basically, but showed this alarming thing that we can have true theorems that are true or false. We can't prove it, right? There's sort of if we start with axioms, we can't get all the way out to these guys out here, which is really strange. That's super, super strange. I think Strogatz will say something about that. So there's this idea of a strong form of emergence, right? That some things can't quite be analytically deduced. We have these proclivities for analytical deduction, right? So that we can write it down with mathematical things, and that we feel that that's really powerful. We can trap it on a page in that way. And then if you can simulate it with a computer, that's a little further away. And in some fields, people don't want to have anything to do with that, right? Economics has been a bit like that. They're a little reluctant to, and it's fair enough because some simulations can be all over the place, all sorts of quality. If it's analytic, you can go through and work it out. So you could talk about these two types of emergence, and some people will talk about more, but this is enough, right? So this is just so you have a handle on these words. So again, this more is different things. So the macro behavior is different to the anything that's contained in the individuals, but the way they interact gives that macro. So that's a weak emergence. It should be explained theoretically. This is much more like magic, right? So somehow you can't deduce it, right? You can't simulate it. Yeah, I mean, maybe the human brain is a good example of where we're really wondering if we'll ever be able to even just replicate it, right? Simulate it somehow. Not sure if we should. That's more like magic. Now, lots of people go on and say, well, this is reductionist, blah, blah, blah. Things are reductionist, no good. It is absolutely an essential part of science. I mean, I've talked about it many times. This is the way we do things, right? So you explain weak emergence by reducing the system and figuring out how things stick together. All right. Magic explains strong emergence. It's not good. And that tends to be the way we think. I mean, as time goes by, things that we think are magic, we eventually understand them, and we replace that magic with a mechanism. But that's tough. That's usually how it works. But it may be that we get to this point where there is a mechanism, we can't really figure it out. So I have another piece from Radiolab to play. This is about 10 minutes long, I think. And so this connects in a bunch of different ways. So Josh Bongard, who will be on Tuesday, who will be here on Tuesday, is one of the people who helped build this thing called Eureka that you'll hear about here. Mike Schmidt spoke at our TEDx meeting event thing, Big Data, Big Stories. That was in 2011, so he's part of this team. And Hod Libson, who was a brilliant guy. So they're all in robotics, but they do all sorts of other things. So bless us all. Okay, so this is from Limits, which is, Radiolab goes up and down, but this is a this was a particularly great piece. So it's human limits. So it starts off with actually, the first section is physical. So it's an Ironman triathlon. And it's got a couple of people who crawled across the line, famously, on live TV sort of thing, after winning the race almost, but then just falling and dragging themselves over, and talk about that kind of psychological thing. They have the fellow who won Ride Across America 5 times in a row, a Slovenian guy, who, that's extreme, right? That's really, really, really extreme. So about, I think it's 7 or 8 days into that race, he in particular would be basically completely insane, right? So, and they would play off this, right? So he was allowed to choose his music and 2 other things, something like that. You'd hear it if you listen to this. And that's it. They governed everything else about his behavior. So this guy's just riding his bike, and he's got the support team. And there's something where he starts talking about Russians trying to, so he was in the Slovenian army, the Russians are coming through the woods to get him. And they said, yes, they are, right? So they would play on this. Anyway, lots of different examples. There's the famous story, I believe this is all true, there's a Russian fellow who could remembered everything. Do you know this story? This guy who remembered essentially everything basically had this amazing video recorder in his head. I mean, it's only 3 pounds, right? So it's kind of interesting as to how much data you can put in there. So that's laid out very well. It's actually quite a long piece, but he became kind of a show, right? So he would go to a big auditorium, people would talk for 10 minutes, just shout out all sorts of things, and then he would reproduce it all, right? Apparently he read Dante's Inferno in Italian, which he couldn't speak, in a cafe, and then could just reproduce the whole thing, right? So he was a synesthetic as well. So he would, as things were happening, there'd be all sorts of colors and things would just sort of happen for him spontaneously, so he could kind of just rewind and reproduce it. Now, it ended up being a problem. It ended up being kind of a disaster because he wasn't able to filter things, right? So his head, in some sense, got clogged, right? So that, very important, I said this before, but about psychology is being able to forget, right? Because part of what you're doing in that is, obviously we make mistakes and we forget important things, but you're sorting things out and you're creating your human narrative in the funny way we do. So that's in there. It's a fantastic piece. And then this last piece is about science. So it's a limit to science. So we will listen to this, and I think it's about 10 minutes long. And then I'll talk a little bit about projects, and then I think we're good.
Hey, I'm Jad Abumrad.
I'm Robert Krulwich.
This is Radiolab, and this next segment began with a simple question.
Mm-hmm. Seeing as our topic so far has been limits, and we've done body,
and we did the brain.
Now we're going to go really big.
Yeah.
Yeah, so we called up Steve Strogatz, mathematician at Cornell University, frequent guest on the show, and we asked him,
are there limits to human knowledge?
Yeah. And his answer sent us on a little adventure.
Is there anything that's at the limits of our knowledge is a question that a lot of us scientists worry about. And certainly the 20th century taught us that there are many things that limit our knowledge. For instance, the Heisenberg uncertainty principle in quantum physics showed us that you can't know the position and momentum of a subatomic particle at the same time. You just can't do it. It's not a matter of not having good enough instruments or not being clever enough. It's just a fundamental barrier that nature puts in your way. In logic, Gödel's theorem tells us you can't prove certain things even though they're true. So there are all kinds of limits, but those seem a bit remote from everyday experience. And yet, I think there are really important limits on our knowledge that we're all familiar with. What I'm thinking of here is our inability to think about big numbers. Because with your fingers, you've got 10, normally. So we're good at 10. We're barely good at 100. And once you start getting to thousands, millions, billions, and trillions, it gets hazier and hazier. When you hear now about the trillions of dollars in the deficit, or whatever it is, the debt, that means nothing. How are you supposed to think about that? Now, when you ask, why can't we understand the common cold, but we can put a person on the moon? It has to do with large numbers.
Not just large numbers of numbers, says Steve, but large numbers of things interacting.
That there are so many genes involved and so many biochemical reactions involved. Our brains are limited. Our memories are very limited. And so I worry a little bit that that we might be approaching the end of our ability to have insight into certain kinds of questions.
What Steve means by the word insight is not like he found the answer. It's like that.
It's like a feeling.
Right.
You know, like that, oh, I get
The
it.
feeling you get when you really understand the answer.
Yeah, that satisfying feeling that I can see the reasoning.
I can actually feel it in my bones.
That's a very pleasurable feeling, but one that we may not always be able to enjoy.
I mean, you can see the space. Good luck.
We weren't really quite sure how to feel about this, but then Steve said, yeah, don't take my word for it. Talk to these guys that work down the hall for me. You'll see.
Yeah, we can go right ahead.
Cool. Can you guys introduce yourself? Tell me who I'm talking to?
Yeah, so my name is Hod Lipson,
My name is Michael Schmidt. I'm a PhD student.
and I'm a roboticist.
And Hod and Mike have developed this thing, which does make you wonder if Steve's right. It's a computer.
Yes.
Actually, many.
A whole tower of computers that are all grinding away and performing calculations.
Actually, when you get down to it, it's just a piece of software, but they've named it
The Eureka.
because that's what it was designed to do, to have eureka moments.
Maybe a kind of simpler example.
And the story of Eureka begins pretty simply,
Let's think of
with a
regular pendulum, okay?
with a pendulum.
Just one of these things you see hanging off a grandfather clock.
Okay, I've got a regular pendulum swinging in my mind.
Okay, swinging left and right.
Now, says Hod, double it. Instead of a string connected to a ball, make it a string connected to a ball, connected to another string, connected to another ball.
Which is basically like a double pendulum. The cool thing about this is you just put it up, you lift it up and let it go.
And what you'll get, says Mike, is
Chaos. This really crazy behavior.
instead of nice and even, now you got random.
It's almost impossible to actually try to predict where this thing will move.
So what they did was they got a camera, connected it to Eureka, and basically just had Eureka watch this thing, move about crazily. And then they asked the computer a really simple question. Can you make some kind of sense out of this erratic behavior? Like, is there something in this system that always stays the same?
Tell me, what about these pendulums over time is not changing?
Because with everything, there's got to be some kind of logic in there. So you're looking for a law, basically. I mean, you're looking for the law of the double pendulum.
Yes, that's the idea.
So Eureka is there watching this pendulum,
It was about 3 a.m. in the lab.
and it's basically spitting out all of these different guesses.
It's formulating hypotheses.
It's getting closer. Closer.
And then onto the screen pops this simple formula. F equals ma. What is F equals ma? Is that actually the law that...
F equals ma is Newton's law of motion.
The Isaac Newton.
That's Sir Isaac to you.
It's a basic law of physics.
And one of the greatest discoveries in the history of human thinking.
Took it about a day, 24 hours. But the interesting thing is that it came up with this thing without knowing anything about physics, nothing. That's why we think that this algorithm might be able to find new laws that we don't know about yet.
In fact, once word got out about Eureka,
That's when the emails started.
A couple emails a day.
From scientists all over the place who were like, hey,
do you mind if we borrow your robot?
for what kinds of stuff?
Anything you can think of, from trying to predict behaviors of cows in a herd, to particle physics, to the stock market.
And this is when we get to Steve's point about the limits of insight.
That's when they met this guy.
My name is Gurul Soel
Gurul is a biologist.
at the University of Texas Southwestern Medical Center.
He got in touch with Hod.
And he said, I have this amazing data, which is single-cell dynamics.
Meaning he's got this tiny little thing,
It's a simple bacteria.
really basic,
And he's been collecting this information on how it works.
on its inside.
How things go up and down. Certain nutrients increase, certain nutrients decrease over time, just like a pendulum.
But the thing is, in a cell, it's like thousands of pendulums.
There's so many parts.
Genes turning on and off.
Thousands and thousands, tens of thousands.
Proteins turning on other genes, nutrients going up and down.
It's this crazy quilt of complicated feedback.
And he wanted to know, inside of this cell, how are all of these things related? I mean, we can measure it all, we can see things going up and down and all that.
But what are the rules?
What are the rules?
Yeah.
And this, he says, is the problem for biology.
Biology is one of the least well understood systems compared to, let's say, chemistry and physics.
They're still lacking the basics.
So we said, look, Mr. Robot, can you tell us what you think are sort of the important principles governing this organism and maybe detect things that were hidden from us.
So he sent us the data, and we analyzed it. And
well, okay, let's not let. Yeah, so what happened?
Suddenly, equations started popping out.
Almost immediately.
The robot came back to us and said, okay, here's a set of 2 equations that describe your data.
Do you remember by any chance what the actual equation was? Not that we'd understand it, but just sort of to hear it said out loud.
Yeah, no, I don't. I don't have my Rain Man skills developed to that degree yet.
The important thing is that the equation was telling him things like, when this protein goes up, this other thing always goes down. And when that thing goes down, this gene turns on and then does a loop-de-loop. And when he went to his cell to check all this out, the equation was right.
These equations matched the data. And in fact, they explain new data.
These equations could even predict what the cell was about to do. But, hold the champagne, there's just one little problem here. The formulas check out, but...
we don't know what they mean.
You don't know what they mean.
Right.
Meaning they don't know why these equations work.
Why when this goes up, does that go down? Why when that goes up, does this go sideways? Why?
I had to first look at this and try to make sense of it. We said like, oh, okay, I think we understand. And we're like, oh, maybe we don't. We think that we're close to understanding it.
But now we're in this bizarre situation. We can't even publish it right now because we can't just publish a equation without explaining it.
So in the end, they're in this awkward position where they've got the answer, but they don't have the insight.
And I think it's a preview of what's to come in science.
The more we turn to computers with these big questions, the more they'll give us answers that we just don't understand.
We'll be faced with this challenge of having to find ways to get a computer to explain what it found.
But that will leave us, if this really happens, in some weird position as bystanders where we're sort of listening to the oracle, but not really understanding the answer. Is there going to be a time when we can't cut it anymore? We've had this window in human history when we could not just know things, but actually understand them. That is, you could know why they were true, not just know, but to know why. And that's a beautiful moment in human history, but I feel like it may only be a moment.
Well, I don't really see it quite that sort of sad and dramatic, because at the end there will be simple principles to describe even the most complicated of processes.
So you have a bias that prevents you from feeling the kind of despair that Steve feels and that we were hoping you would feel.
Oh well, I have a positive outlook.
Well, I'm just wondering about the we. Look what we have discovered, you'll say when you're an old man with your robot sitting there in a dress next to you. And the robot will be holding your hand, but that will be a cold hand. And Jad and I will be thinking, I don't know, who's the we here?
Well, I would say we is sort of knowledge. I'm just thirsty for understanding and thirsty for knowledge. Me and the cold hand holding my hand, we've accumulated and contributed to the overall understanding of something that we thought maybe 50 years ago wasn't possible. And that would be something that would make me happy.
Hi, this is Steve Strogat. Radio Lab is produced by Jad Abumrad.
Our staff includes Ellen Horn, Michael Raphael, Soren Wheeler.
All right. So a little sad there from Strogat, but this is, I don't think I never saw this coming, I have to say. I mean, I came through with physics and engineering and so on, and plenty of computers, but this is a very odd situation to be in. And this thing, Eureka, is being used more and more and more. It's become a very popular piece of software.
I think the software stuff.
Oh, that's true. They do. Yeah. All right, I'll fix that up for you. I know they want to be clever. Why did they do that? Branding. Yeah, so really, it's an interesting time. I think there's it's kind of like Gödel's theorem, right? Gödel's theorem, you could imagine Gödel turning up and saying, by the way, you can't do everything. It didn't stop mathematicians at all, right? They're still just marching out into these, these frontiers, and that's going to be the same for science. But it's possible that some systems are just It'll be too hard to understand. All right. So emergence. That's the story of emergence. I have some more things about emergence. As you can see, there's some stuff here from Poland, the emergence of taste and so on, but we can come back to that. All right. So there is this set of slides online now, and I'll talk about it a little bit just for the rest of this lecture about projects, right? So you guys can look through this. I suggested maybe you could work in groups of one of two if you want, but I'm not sure. Maybe that's up to you guys. If you want to work by yourselves, that's totally fine. So again, it's not going to be the fifth week. All right, so it's a bold statement. But the idea is that we will have at some period, it's in the syllabus I put together. You have these 3 to 4, depending on numbers and so on, 3 to 4 minute introductory talk. And so that sounds like that should be very easy, right? It's just 3 minutes. But this is actually a well-used kind of convention at different kinds of conferences, and it's a powerful one, right? Because you have to get your message out there, and at conferences, stat mech ones in particular, they're quite serious about it, right? You get the gong and you're gone after 3 minutes. So there are some people who, you know, they're just revving it up, and they're talking about their abstract or something. And so it's definitely something you can practice and so on. But this is a very powerful thing. So it fits into that narrative hierarchy thing that I like to talk about, right? So you need to be able to tell your story at all scales. But that's, you know, you don't have to have solved anything. So there's a final presentation and a report, 5 pages. The idea is heading towards journal papers. That's really what I'd be thrilled to see. Not necessarily at all. Of course, you can have anywhere between these things, right? So it could be research papers. As I said, we have 15 now. We'll probably have 20 to 25 in about a year's time coming out of this course, or, you know, connected or adjacent to this course. But you could certainly do this, where you take, and I'll give you some suggestions of papers, because these are fun to talk about. Some work that's been done recently that may seem interesting to you, that's important, maybe controversial. Just understanding that would be a fine thing, right? So I've talked about this narrative hierarchy. Business, that's what we're up to. Lots of things. So we actually have, Computational Story Lab, we have a couple of team members. If you want to be involved in that, we can talk about it. So we work on lots of different systems. I think everything is in there. And so we have Twitter, but that's not everything we're about. This is just to show you that there are humans on Twitter talking about food in a very reliable, spectacular way. Swearing goes up through the day, really nice. And our measure of emotion, right? We have this measure of happiness. What you see is it actually goes down during the day, but the emotional spectrum widens out, right? So we become more emotional, more unhinged, basically, and we need to be rebooted at the end of the day. So basically, we're like the Windows operating system. Yes. With Unix, we'd be just rock solid. Okay. We'd be awake all the time, just doing things. Okay. And occasionally get hacked. Yeah, okay. Yeah, but breakfast, lunch, and dinner. Awesome. Okay. So yeah, there are more here. I don't have others. I want to tell you this. So if you have hungry, starving, eat, food, they all follow the same shape. They have different relative abundances. So does chicken, which is, you know, bad for chicken. Pizza is different. Pizza is a different thing. Anyway, people. This is something that we could talk about. I mean, I have a number of ideas here. This is something that I've been involved in. We'll talk about some of these things in the course. But online experiments to study social behavior. There's just looking at how people behave, but there's also creating ways of, and I have some examples of solving problems using people, right? I mean, we have these kind of more slightly bad ones, you know, the ones involving the very simple ones, say that the captures and recaptures, right? That's using people in this distributed way. But there are some problems where we've made great advances by by people and computers interacting in certain ways. I mean, actually, Google is, in fact, a very good example of that, right? It's not, we tend to think of Google as this great algorithm sort of thing, but it's actually, it will traditionally work very well. It's getting more and more messed up, I suppose, but people made links between sites, right? And they were meaningful links, and that's what the algorithm worked on. So it was very much a socio-technical computation, right? There's lots of different things. Collective search, which we'll come back to later on, the collective detective thing, you know, all sorts of things, cooperation, cheating. I did want to go on about that piece before. We had the sort of the emergence of badness collectively, potentially, right? So people combining it in certain ways to the Schelling story, right? So I just wanted to say something extra about that, which is that the conventional kind, or the sort of the thing that usually we're most concerned about when we think about people joining together is that, academically at least, is that people are locally bad but somehow cooperate globally, right? So that's a way it's framed, the myth of global cooperation. So you'll see that a lot. I think the opposite is more important, right? So people behaving well together, creating some evil cooperative whole. And you know, both things are possible. And the extra piece is that I think the first one is so entrancing to academics, right? Why do all these selfish individuals? I mean, we have all this, like the selfish gene, and all, you know, we have this really. Why do all these selfish individuals somehow? You know, why does society kind of exist? You know, it's because you have a very odd set of people who are studying these things, and they're selfish, psychopathic academics who have, you know, killed everyone else to get to their position. So they see someone else helping someone, and they're like, why? You know, that's enigmatic to them. You know, they don't understand. So that's why it's talked about so much. It's because you have a certain type of people studying people. Anyway, so I call this the play project, right? This is my thing. People play. It's one of our great things. Hunch and crunch, right? So that rhymes. I had play and crunch, but hunch and crunch rhymes, right? So we're the hunch things, we're the play things, and crunch is computers. So there are lots of good examples. There's a link here. You can look at all the papers we've been looking at in complex systems reading group. That's another piece. This is just the start of work that has emerged over time. So this is actually the movement of dollar bills around the US using where'sgeorge.com. Some of you know about this, right? You see a little stamp on a dollar bill, which is illegal, and you'll go to jail. But if you put in the little number, that's what do you call it? What's the number on a bill? Serial number. What is it? Yeah, right? You enter that, and you can see, and I think maybe 15 or 16 times would be sort of about the maximum that a bill has been entered. So these are bills that started in Seattle and ended up all over the place, right? So very interesting study. It was Dirk Brockman, who was at Northwestern at the time. And so you'll hear about random walks in those next lectures that are online. Subdiffusive, superdiffusive behavior, right? So there are these big jumps, but the way time works with these is different. Yeah?
Isn't it also possible that there's just 4 different places that stamp the bills? So for them to go anywhere, they have to have traveled from those.
So these are just 3 examples they've made for the figure? Is that what you...
No, like these bills, somebody owns a stamp that stamps them.
Oh, I see.
There's just 3 people.
I mean, technically you can go online and put any
Yeah.
bill.
If you know about it, people will do it. They advertise a little bit by doing that as well, yeah. But in principle, you can do it, yeah. I mean, yeah, right. So if you know about it, people get excited. They hear about it, they open their wallet and get out all the dollar bills and put them all in. That's kind of how it happens.
Register twice.
Yeah, for it to be then interesting. But actually, just so you have those 2 pieces of data, it's pretty good, right? So you have time and location, and you add enough of those things up, you can get the whole story. So this is then, so Jim Bargrow might talk about some of this. This is using cell phones to locate people, right, based on when they call. This is some unknown country in Europe that called up the Barabazi group and said, we have data, we love your work, we will give you unreal amounts of data from our customers, and not tell, and you can never tell anyone where it's from. So he has all sorts of things, just about quotidian, everyday movement of people, but also then how they respond to emergencies. Then there's more work now about migration, how people move, and it's not that kind of, I showed you the zip story of the gravity model. It's different to that. That's an excellent paper, Simony, you could work on that, who's I think a colleague of Bagros. So this is a really interesting, fantastic data set, really, really interesting. Lots of good things in there. This has been a bit controversial, control of complex networks. So there's all these different types of networks. So there's everything from like yeast networks to some corporations and organizations. There's a bit of like everything that you could throw in there, looking at how you might be able to, what's the minimal set of nodes you need to be able to control the whole thing. So this is if you want to control the world type person. If you've got your white fluffy cat that you stroke on your swivel chair, this is a good paper for you. So this is the hunch and crunch type stuff that I was talking about. A great example of it. So protein folding, right? Very difficult thing. What people had set up was using the kind of the SETI approach, right? The search for extraterrestrial intelligence. Of course, we need to search for our own intelligence first, but was distributing all of these programs onto computers, and so you're a volunteer scientist. You're helping out. People were able to watch the thing trying to fold the protein, right? So that was kind of one of the, wasn't just sitting on your computer crunching away. They give you a nice little visual. People started to write into these guys running the thing that it was horrible to watch because this stupid thing should obviously just, like, it's obvious that it should just do this, but it couldn't use it with it couldn't get there with the search thing. So they changed it, they gamified it, and lots of things have been gamified. Lots of things have always been gamified, but this has turned out to be very productive. So people are creating little algorithms for how to make it fold. And then those algorithms are being combined by each other, so there's a whole sort of extra levels of things. That's fun. The Zooniverse is another one. I talked about captures. ESP game is from the Louis von Ahn. That's image tagging, right? So you go onto this thing, there's an image in front of you, and you have to say, it's a bit like Family Feud, right? So you have to, which you should never watch. So you have to say words that you think are inside, to describe this, right? So if there's a cat, you say cat. And if the other person says that, then you get a match. It's a very clever thing. So basically you have to think, what would a random other person think? Not what would you would think. And if you match with random other people who are thinking about matching other random people, then it will work out. And so if you put in bad words, then it's unlikely they will put it in. So it's nicely done. So Zooniverse is very similar to Foldit. It's emerged out of, again, this massive data story, right? So too much data, can't sort it out. Trying to find and identify galaxies, let's ask people. So this is a really beautiful thing, actually, right? The citizen scientist has always been a big part of astronomy. I found a meteor, or I found a planet, whatever it is. And you write in your letter, and you're out, this sort of bird-watching character people. But this is now the sort of the modern version of it, which is you go online and you look at things and you say that's a spiral one, or right. So people are helping out again at this very different kind of astronomy. But they've expanded. Now they have things like identify whale songs and look at ancient parchments and try to translate them and so on. So that's building a whole story there as well, which I think is fantastic. This is we have some nice work by Paul Hines here on this topic. A lot of us are adjacent to this work, talking about failures. So you have coupled networks, failures of in this case power grids from a communication network sitting on top of the power grid, failing. Again, controversial work, simplified models. A bit of a toy model. Maybe it doesn't do what people really think. But clearly, this is the right framing, right? We have to understand how these interlocking networks work. So that's a good paper to start with. As I said, I'll just probably stop here, but there's lots and lots of other things in these slides. This is an example of, so Jonathan Harris does so many great things, but how people move around, right? Or how we now move around, how geography works for us, right? So if you're in the 10,000 years ago, you have to walk, right? You have to walk. So your sense of geography is very two-dimensional, depending on how rugged the landscape is. But if you like, if you measure in terms of time as you go out from your place and you're, right, then the available, or what you reach, grows like r, right? So this is 2 pi r. So the number of places, or 2 pi t if you like, it's proportional to this. But if you allow then people to fly on planes and then they start to do this, right, and they pop over here, then you're reaching many, many more points at a particular time. So the number of points that you can reach at a particular time, right, so if it's just going linearly, then it's like you're in the desert. And if it's going square, then you're in some sort of higher dimensional space. And if you start in New York City, you get to a lot of places pretty quickly as a function of time. So what is modern geography actually like, given you have lots of money and you can fly on planes? But that's a descriptive thing, but it really matters tremendously, of course, from disease spreading point of view. And a lot of the big models now, or the big real system models, of course, incorporate airline travel and so on. But I think that's just an incredibly interesting thing. Okay, so lots of other stuff. Boom, boom, boom. You can just look through it, blah, blah, blah. Lots of things. That's like whether things explode. Lots of networks, blah, blah, blah. Networks, geography, blah, blah. That's how people form terrorist groups and break apart. This is great stuff. This is fantastic. This is a great economics thing. This is a really good piece. And so this is connecting countries by where they are in product space, right? So are they similar in terms of the products they make, and what can they move to in the next time steps, or the next 10 years, or the next, right? So they're adjacent to it, right? You can't just jump from selling bananas to nuclear reactors. And so on a database way, this has been sorted out. Hidalgo's at the MIT Media Lab now, beautiful work. Lots and lots and lots and lots of other things. So anyway, so look through that. Give me a project and we'll talk about it, okay? So I'll be back in 2 weeks, and please look at those videos. I will send you emails about assignments, and there'll be something due.
Will you post solutions to the homework?
I will, yes, can do.
Oh, yeah,